Well, hello physics folks, and welcome to Doc Onco Physics. Keith Onco here. Today what we want to do is we want to take another look at projectile motion problems or kinematics in 2-dimension. Today's problem is going to be a problem where a football player or a soccer player kicks a football or a soccer ball starting at, oops, switch pens here, starting at the ground position, goes up into the air, all right, and then lands at the ground position again. Okay, and we would like to know the range, all right, or the final position in the x direction for our football. Okay, once again, we're going to take our starting position in the x and y direction to be x equals 0 and y equals 0. Okay, because we can decide wherever we want our coordinate system to start, that's our option. Okay, so let's start filling in our table with the information that we have. Well, up here in our diagram, it says that our football or soccer ball is kicked with an initial velocity of 31 meters per second at an angle of 30 degrees to the horizontal. Okay, so like we've said before, we are only dealing, all right, if we look at our table here, we're only dealing in x and y coordinates, okay, x and y data. If I'm kicking a soccer ball or football at an angle of 30 degrees, that's not either x or y. And so we're going to have to break this up into its x and y components. So what I've got here is I've got a football. It takes off at 31 meters per second, and I need to know the x component, and I need to know the y component of that. So VIX and VIY. And the angle here is going to be 30 degrees. So how do we do that? Once again, we're going to use trigonometry, right? We're going to use the cosine function because cosine is the adjacent side to the angle. That's this side. And we're going to use the sine function. The sine function is the opposite side to the angle. All right, the angle is being right in here. Okay, so VI in the x direction, our initial velocity in the x direction, is going to be 31 meters per second times the cosine of 30 degrees. Okay, and when I do that math, what I come up with is 26.8 meters per second, and that is in the x direction, the positive x direction. So I'm going to put this in here. This is 26.8 meters per second. Okay. How about the y side? Well, VI in the y direction is going to be 31 meters per second, again, times the sine of 30 degrees, and that's going to be 15.5 meters per second. So I'm going to fill that on the y side of our table. Now also notice that the football was being kicked, all right, I'm going to do this in red, kicked in this direction. All right. If I want to find my components, right, I have to start at the beginning of the resultant vector, all right, and then draw in my components. Well, I have one component that goes to the right, that's the only way to get there, and then one component that goes up, that's the only way to get there. I have to make sure that my signs are correct. So the sign for the x vector, since it's going to the right, is going to be a positive x direction. And the sign for the y vector is also going to be positive. It's positive in the y direction. So we have positive plus signs for both of them. This is very important as we deal with vectors and we deal with directions of things that are moving. Okay? In this case, they're both in the positive directions. Okay, so we have our initial velocities. So let's take a look at what else we know. Well, because we said our coordinate system is starting at the 0, 0 position, we can plug in zeros for the initial positions, both x and y. The final position in the x direction is what we're looking for, right? We're looking for that range, all right, x final. We want to find that out. All right, so we don't know that. How about the final position in the y direction? Well, it starts out in the y direction at y equals 0. Where does that end up? Well, the football travels up and down. And where does it finally end up? In the y position is equal to 0. All right, so our final y position is 0. All right, so that's going to make things a little bit easier when we do some of the math. If you're not sure what the final position in the y direction is, if you take the picture of the person kicking the football and you make believe you're in the position of the football player, right, and you look at it from that dimension instead of the dimension that we're looking at it from, the football is just going to go up, it's going to go up, and that's going to come back down. And it starts out at this position and it ends up at the same position. Okay, so we know that. How about the final velocities? Well, final velocity in the x direction, because once the football player kicks the football, that's the only force on the football in the x direction. And so there's no other forces, and so our acceleration in the x direction is going to be 0. All right? Again, we're going to neglect air resistance. And so our final velocity in the x direction is going to be the same as our initial velocity in the x direction. It's going to be 26.8 meters per second. Okay, because remember, acceleration is the change in velocities. If you have no acceleration, you have no change in velocities. How about v final in the y direction? Well, we don't know what that is. Okay, and we don't really need it in this case. We could find it, all right, but we don't really need it. So what we want to do is, using our y direction data, we would like to figure out one of the only pieces of missing data in our table. We'd like to figure out the time. And we'd like to do that without figuring out the final velocity first. Well, which of the equations in the upper right-hand corner have time in them? Well, the first one does. Right? We know x final in the y direction. We know x initial in the y direction. We know initial velocity in the y direction because we've calculated that now. We know our acceleration is negative 9.8 meters per second squared, always in the y direction. And t is the only variable left in that equation. So we could use the first equation. We also have time in the second equation, all right? But we don't have our final velocity, all right? So we're missing two things in that equation. We're not going to be able to find time. Could we have done this in the same way we did the last problem, where we find out our final velocity using this equation first and then plug that into the second equation? Yes, absolutely. That's perfectly valid. But we're going to use the first equation this time just to do things a little bit differently. So let's find out time. Well, our x final in the y direction is 0. All right? Our x initial in the y direction is 0. So 0 equals 0 plus our initial velocity in the in the y direction is 15.5 meters per second times time plus a half times a, negative 9.8 meters per second squared, times time squared. Okay, so we plug the values into the first equation. What I'm going to do is I'm going to move this to the other side now. So I get negative 15.5 meters per second times time is equal to negative 4.9 meters per second squared times time squared. Okay, this time over here is going to cancel out with the exponent up there, and I'm left with negative 15.5 meters per second equals negative 4.9 meters per second squared times time, and our time turns out to be 3.16 seconds. Okay, so there is our time. Now, what am I going to do? I'm going to plug this right into my table. 3.16 seconds. And remember that time is the same on both sides of our box here. So the time in the y direction is also the time in the x direction, 3.16 seconds. All right. I could find out the final velocity in the y direction. I'm not going to find that out right now because what I'm interested in is the range in the x direction. Well, I've got lots of information in the x direction now. I've got my x initial, I've got initial velocity, final velocity, acceleration time. I've got all kinds of stuff. So I'm looking for x final. So the best equation to use would be the top equation. All right, x final equals x initial plus v0t plus a half at squared. So let's go over here. All right, let's figure out our x stuff. Well, x final is going to equal x initial, which is 0. And remember, we're using the same equations, but now we're using only our x information. We can't mix x information and y information in the same equation. So it's only on the x side now. So x final in the x direction, should put that there, equals 0, plus v0 in the x direction times t. Well, v0 or v initial in the x direction is 26.8 meters per second times time. Well, we just figured out the time to be 3.16 seconds plus 1/2 a times t squared. Well, a in the x direction is 0, once again, times t squared seconds squared. Okay, this side is just going to drop out. Okay, so x final, or our range in the x direction, is just going to be 26.8 meters per second times 3.16 seconds. And when we plug that into the old calculator here, I get 84.68 meters. And that is our range. So that's a pretty hefty football kick or soccer kick, almost 85 meters. So that's how we solve a problem, another problem in projectile motion. Again, what are the keys? The keys are breaking up any data that you have that is not strictly x or strictly y into its x and y components. That was the first thing we really had to do. So we had to break up our initial velocity up here into its x component and into its y component. Once you do that, it becomes a fairly simple problem where we calculate y data first, then we bring it over and we calculate x data, and we complete our table. Well, I hope that helps. I'll see you next time.